In this video, we want to learn about the linear least square regression. So the simplest example of the least square approximation is that if we fit a straight line to a set of observations. So let's say our observations are like x1, y1, x2, y2, up to like xn, yn. So if you want to write down the, fit a straight line for this one, the mathematical model of the expression that we can use for this data is going to be, let's say it's going to be y equal to a0 plus a1 x plus e. This e is the residual or error, because this is the one that we are fitting a line for it, right? So there are going to be some distance between the real value and our prediction. So this one is going to be, we call it error or residual. And let's say the situation that we have is like this. Here I have my x and y. Right? So this point here is x1, y1, and then I have another point here as x2, y2. I'm going to have like a few points like this. Right? So x3, y3, these are the set of the observation, when we say. And now I'm going to have a line for it, like let's say this is the line that I'm going to fit for it. And the equation for this line is going to be like, it has a intercept, and then there is a slope for our x, right? Plus e. Because you see that this line doesn't overlap exactly on this point, so we are going to have some error for it, like residual. So when you think about it, it's like that. Let's say I have one line like this. I would have another line which is like, let's say like this, or another line like this. If I ask you which line you are going to choose, what would you say? Think about it for a moment. It's like that. I have one line like this, another line, let's say like this, and some other lines as well. So which line would you choose? Think about it for a moment, and then you can pause the video and come back. So we are going to choose the line that it has the minimum error, right? Because this E is like that, let's say it's going to be the difference between this one and this one, or difference between this point and this line. So we are going to choose the one that has the minimum one. So what I'm going to say is like that, I'm going to write down this E to see that how would it be from this equation. So E is going to be equal to y minus a0 negative a1x, right? So that's going to be my E. And then I'm going to find out because when you are looking at these lines, I'm going to keep the main line that we had while we are working on it. It doesn't mean that this is the best line. I'm just keeping one of the lines that I could show the information on. Okay. So here, E is the distance from here to this one, right? So my observation and the prediction, whatever it is. So here, when this one is negative, right? So when you look at it, this one is negative, this one is positive, positive, negative, negative. So what are we going to do? We are going to square this one, all of this, and then add them to find out because we don't want this, let's say if this is the positive and this is negative, if you want to add all of these distances, you don't want them to like remove each other, right? So what are we going to say? We would say sum of a square. So sum of a square of residual, and we show it by the sum of a square of the residual is equal to, right? And then I would have the sum, right? And the square of this residual. So this line, we said that this distance from the line, we said that this is the residual. So it's going to be sigma, all of these E that I have, and I have a set of data is like x1, y1, x2, y2, up to xn, yn. It means that I would have n residual as well. So it's going to be ei, I is equal to 1 to n. Okay? So this is going to be the equation of the sum of the square of the residual. And then I'm going to replace this equation, this part, instead of this E. So it's going to be equal to sigma yi minus a0 minus a1 xi. And sigma is equal to 1 to n. So this is the sum of the square of the residual. Next step is that we want to find out this a0, which is the intercept of this equation, and then we want to find out the a1. So now think about it. I want to find out this sum of the square, I want to minimize it. So this one, we want to minimize it. So when we want to minimize it, in fact, when we want to find it, it's like that we are going to get the derivative, right? And then make the derivative, like say that, okay, the derivative is equal to 0. That's going to be the point of the, that we have the minimum amount of this equation. So for getting out the derivative, we have a0 and a1 as two variables that we want to find out right now, right? These are the things that we are looking to find out. And so because there are two, so it's going to be partial derivative. In fact, we want to get the partial derivative of SR respect to the a0 equal to 0, and also we want to have the partial derivative of SR respect to a1 equal to 0. Okay? Because when we do this, and then when we find out the a0 and a1, those numbers is going to be actually the numbers that if we put it in this equation, is going to give us a line which has the minimum amount of the residuals comparing to the different lines that we are going to have. So with this one, we're going to find out after we get the partial derivative of this and partial respect to a0 and a1, we are going to find out the value of the a1 and a0. That you can, I'm going to write it down here. So for a1, these are the final value of it. So a1 is going to be equal to the n sigma, I have it somewhere, xi yi, and then minus sigma xi, sigma yi, and then divided by n sigma xi power 2 and minus sigma xi, all of that power 2. So that's the a1 when we get the partial derivative and equal it to 0 and solve the system. And then we have the a0. For a0, we can say that a0 is equal to the y bar minus a times x bar. So in fact, it's like here. So I'm looking for this. So I would say, okay, so if I get the average of y and average of x, I can say this a0 is equal to y bar. We would move this a1x on the other side. So it's going to be y bar minus a1x. So it's a y bar minus a1x. And then here, instead of a1, we are going to put the equivalent amount of the a1 just for y bar and the x bar in another video, which is about the simple statistics that we needed for the curve fitting. We learned about the value of these means, which is going to be, for example, this one is going to be equal to the, instead of y bar, I'm going to write down sigma yi divided by n, and then a1, and for x bar, I would have sigma xi divided by n. A1 is from here, right? So with this equation, I can find out A1 and A0. Then I will put the A1 and A0 in this equation, and we are going to find out the best equation or best line for fitting to this one. There is just one more thing before going to an example, and that's that when you look at the SR and the sum of the square of the residuals, in fact, we can define the standard error of our standard error of the estimate for the regression line as well. We name this line regression line, right? Because we, in fact, this is my regressor, this X is regressor, this Y is my outcome. So I found these coefficients for my regression line. So we can find out the standard error of the for the regression line, for our estimates for the regression line, and we would just write it down that our. So I'm going to write down a standard error of estimate for regression line, which is this line, right? So this line here, we call it regression line. And we call this method, we call it, it's written here, we are in the category of curve fitting linear least square regression, right? So with this one, we would have we are going to find out the standard error of it, and we would show it by the standard sum of the square of the yx, or the, like, let's say the standard error of the estimate is going to be equal to the square root of our sum of the square of the regression divided by the n-2. This n-2 here is the degree of freedom as well. In the previous video, when we were talking about the simple statistics, we had an example with the chair for the degree of freedom. It's a good idea if you go and look at that one. It's going to help us to understand this n-2 better. So this is the standard error that we have. We can say a standard error of the estimate for regression line, or we can say that's the standard deviation of our regression line. So another thing that we have is like that we need to say that, okay, so I have this regression line as my best estimate. I have my best estimate, in fact, here. And then I want to see that if I can accept it or not based on this sample that I have, like these data points, or I have to change all of the sample, like all of the data points that I have. For that purpose, we are going to, in fact, we want to see that if our best estimate for this sample is that the best estimate for the whole population that we would have. So what are we going to do? We have another coefficient, and we call it coefficient of determination, which is R square. And with this R square, we're going to say that if R square is 1, it means that we are going to cover all of the data points that we have. So here is the coefficient. Another term that we need to use is the coefficient of determination. And we show it by the R square. And the coefficient of the determination, in fact, it's the we are gonna subtract the S of total, the sum of the square of the total, minus sum of the square of the regression, and then we would divide it by the sum of the square of the total. So sum of the square of total minus sum of the square of the regression divided by the sum of the square of the total. And when we say sum of the square of the total, you know what's the sum of the square of the regression, right? So we found it. Sum of the square of the total is very easy. It's like that whatever observation that you have minus your the average of all of those observations, and then a square of it. So in fact, sum of the square of the total is equal to the sigma yi, right, minus y bar, a square of it, because we say sum of a square, right? So it's the square of this one. So coefficient of determination, or R square. And if you have ever worked with the Excel and tried to fit a line, you can see that after you fitted your line, you would have your R square written. Sometimes they show it by the capital letter is the same, that's fine. And we would say that that's the coefficient of the determination. For example, the coefficient of determination is 95%, so we would say that our regression model probably is a good regression line. It depends on, depending on the different experiments and situation that we have, the minimum amount for this determination coefficient is different. Another thing that is good that we cover here is that if we get the square root of this, we call it correlation coefficient. So we would say, or I can write it down in the same way that I wrote it down. I can write the coefficient of the correlation, right? Coefficient of correlation, which is the square root of the coefficient of determination. So R, right, is going to be a square root of R2, which is going to be a square root of the S of total minus S of the sum of the square of total minus sum of the square of regression divided by the sum of the square of the total. So the correlation coefficient helps us to say that, okay, how what's the correlation between the x and y, right, between the variables that we have. And when we replace the amount of the S of total and S and R and S and T, so the equation that we are going to have for R is going to be a lot like larger than this one, because just imagine instead of sum of the square of the total, you're going to put this one. Instead of y bar, you're going to put the value of the sigma y divided by n, and then square it. And for sum of the square of the regression, you're going to put this equation. But for A0 and A1, you would need to find out you would need to write down the whatever you have found for A1 and A0, right? So if our R square is equal to 1, it means that the line explains, it's like the represent of 100% of the variability of the data that we would have. Just be aware of this. It's possible that sometimes we obtain a relatively high value for the R square when the underlying relationship between y and x is not even linear. At the minimum, you should always inspect a plot of the data along with the regression curve, which we are going to learn about these things, that one later. But it's good that you would look at it and see that, okay, so if you have your data points and this is the line, so how good your curve, like your line is going to fit your data points. So the next part that we want to learn is about the curve fitting, but we want to learn how to linearize the nonlinear relations that we have. This was linear, right? So we want to learn about the polynomial regression and those ones. Before going to that, I would recommend that you would go to the example of the linear least square that I posted on the on this channel.